When a modern commercial fleet reaches 100,000 vehicles, a standard tracking setup hits a mathematical wall. If each truck transmits a location update every 5 seconds, the cloud infrastructure must ingest and process 20,000 writes every single second without a break. Most start with a standard CRUD architecture, an API gateway funneling that massive telemetry stream directly into a single relational database. But at this scale, constant disk-level locking freezes the database, latency spikes, queues overflow, and the persistent storage layer shatters. To survive these loads, the architecture must ensure that no single incoming telemetry packet is allowed to wait for a database write. We solve this by building an event-driven pipeline that decouples the vehicle hardware from the dispatcher screen, using a series of specialized intermediary layers. Maintaining sub-second visibility for 100,000 vehicle fleets requires moving the heavy compute burden off the database and directly into the moving data stream itself. The pipeline begins at the vehicle edge, generating raw telemetry through two primary protocols. Heavy-duty J1939 trucks broadcast a continuous stream of diagnostic data, while light-duty OBD2 fleets pulse in discrete segments through request and response polling. Passing through cellular dead zones, onboard hardware buffers telemetry locally. Upon reconnecting, that data hits the cloud in heavy bursts. We manage this through an edge gateway acting as a central broker. The MQTT protocol is perfectly suited here, significantly reducing the computational overhead of re-establishing TCP sessions every time a vehicle reconnects to the network. To maintain security at the edge, the gateway uses X.509 certificate authentication to validate each device before it is allowed to publish its payload. At this ingestion layer, the architectural goal is maximizing connection resilience, ensuring no data is lost during the handoff from the vehicle to the cloud. Post-broker, data never goes straight to a database. It flows into an Apache Kafka event stream, acting as a shock absorber that organizes incoming packets into ordered partitions. An Apache Flink node then pulls those streams for stateful processing. Flink's role is to normalize these fragmented payloads and enrich each coordinate with geographic context entirely in flight. This processing layer also solves the primary issue caused by cellular buffering, out-of-order data. A gap often exists between when a truck records a coordinate and when our pipeline receives it. Flink uses watermark lines to sweep across the timeline, grouping delayed, out-of-order packets back into their original chronological sequence without stalling the live data flow. The result is a clean, deterministic data seed that has been transformed from an unpredictable edge signal into a reliable record. To support a live map, we need to store the current state of every vehicle. We route the processed stream into a Redis in-memory data store, which serves as our high-speed hot storage layer. Storing locations as raw coordinates is terribly inefficient. Proximity queries would force the system to manually calculate the distance for every vehicle in the fleet. We avoid this with geospatial indexing. A quad-tree grid creates corner distortion, making lookups inconsistent. Uber's H3 standard uses equidistant hexagons, ensuring uniform distance to neighbors. In Redis, the geoadd command transforms these coordinates into a single 52-bit alphanumeric string. Converting coordinates into these integers allows the system to execute proximity searches as simple prefix lookups, providing answers in milliseconds instead of seconds. However, keeping this data in memory is expensive, and Redis cannot efficiently store months of historical trajectories for 100,000 trucks. We solve the capacity problem by branching the pipeline. While live state goes to Redis, we offload the full historical trajectory logs to a cold storage layer like Amazon S3. Separating the volatile geospatial state from the historical trajectory logs ensures the live dashboard remains lightning fast, even as the cold storage layer accumulates petabytes. To deliver real-time updates, we expand the architecture to include WebSocket servers connecting to a dispatcher dashboard. But WebSockets are stateful. If a truck update lands on server A, but the dispatcher is connected to server B, the update gets stuck. We bridge this gap with a Redis pub subbroker, acting as a shared nervous system. Flink publishes updates to this central channel, instantly fanning out data to every WebSocket server simultaneously. Server B then matches and pushes the update to the dashboard. This fan-out pattern ensures that our presentation layer remains horizontally scalable, treating individual web servers as interchangeable conduits for the moving data. From start to finish, a single coordinate ping begins on the physical J1939 bus and travels over a cellular link via MQTT. Looking at the full architecture, Kafka queues the packet, and Flink instantly enriches and reorders it. It indexes in Redis, publishes to the FANOUT broker, duplicates across servers, and flashes onto the live map. This entire journey takes roughly 150 milliseconds. This architecture works because it prioritizes ingestion resilience at the edge, while delaying persistent storage until the data has been cleaned. By moving spatial calculations and geofence logic into the stream layer, we protect the core database from the overhead that usually destroys real-time systems. Beyond pure performance, this decoupled design enables privacy by design. Placing a stream processor between the vehicle and the database allows the system to redact driver information or enforce compliance boundaries before a single byte is ever committed to a hard drive. Because ultimately, at this massive scale, the architecture itself becomes the primary tool for both performance and security.